Good morning, everybody. Today, we will give a brief introduction about our project that is GridSight, an AI-powered smart grid solution for the BESCOM challenge on the smart meter intelligence for the loss detection. Our main goal of the GridSight is to transform the smart meter data into a proactive operational intelligence. Today, smart meter generates a massive amount of 15 minutes interval electricity, but most of the it is used in for the general purposes, only for billing or either for basic monitoring. But we, as an entrepreneur skills, have thought about an system that uses AI to predict the localized demand spikes, to increase the high risk grid zones, to detect the anomalies and possible electric thefts, and to provide an actionable insight for the grid operators. Because we knew that we had two. Most importantly, the platform work as complete read-only decision support for our layer. That means it doesn't modify the BESCOM existing infrastructure, means low cost, easy to configure. So now I would explain about the. So first we go through our project. Then we have front end where that is being deployed in Vercel. We have backend that is deployed in the render. Then we have Swagger to check our APIs. We can go through it. Then we'll just go to the data flow, how the user data flow is committing. First, we have the data layer at the top. We will begin with it. It has 50, as we already talked about, the smart meter will give our 15 minutes data to the consumption. Along with it, it will give the contextual information such as weather and the calendar APIs. Then these input would be validated through the pipelining process called as load API, load API and validate, and this stage will be either cleaning the missing values, validating the metered readings, and handles the corrupted records. Then it will go to the intelligence layer. Then this is the core AI analysis layer where the multiple intelligence are using. That is, we are using the residual intelligence for the baseline deviation analysis. Then we have six agent slide detection used for anomaly and theft detection. Then we have context feature that is for weather, time, and locality behavior. Then we have temporal intelligence for the long term pattern persistence. Then we have physical engine that validates the feeder level and intelligence for the lifelong consistency. Each module analyzes the grid behavior for the different perspective. Then we will move forward to the fusion and detection layer. After all the intelligence modules generates the output, the system moves into fusion and the detection layer. What is the fusion and detection layer? Instead of relying on the single model, the system dynamically adjusts the confidence score basis on agent reliability, historical accuracy, and time of the day behavior, and the feeder condition. The fuse intelligence then passed into the hierarchical classification, risk adjusted economics, and the final decision engine that we can see through in this decision level. And this stage determines the anomaly severity, the urgency level, and the inspection priority that we have discussed. That these are the two main problems that we are facing in the grid site, um, in the current scenarios of the smart meters. Then we have the output layer that include the risk map and that we can see, and the action tables and the down label PDF cases. Then we have forgotten about the learning layer. The learning layer will finally, the system will include a learning layer that will inspect the results and operator feedback and continuously feedbacking the platform that will help our model to update the agent reliability and adapt the threshold according to it, and it will improve the future detection accuracy. Overall, our architecture enables the grid site to move beyond the simple anomaly detection as a function and a complete AI-driven operational intelligence layer for the smart grid operations. As we go through our repository structure, we have front end, we have backend files, we have these models that we were talking about. The fusion engine, that is adaptive probabilistic functions, probability function fusion.py, that will be logistic fusion with the confidence intervals, physics engine that would feed the balance and energy conservation, temporal intelligence that will persistent and tracking, and we have economical impact that is for ROI, that is return on investment and expected value calculation, and generate data that would be that we are generating 200-meter BESCOM data sets, but we are using the dummy data, of course. Now moving forward, we, as according to the problem statement that has given to us, that we had two problems. That was no early warning for the demand spike and the revenue leakage to the theft and tampering. So, that we have already discussed how we are conquering it. As shown is the dashboard, we can see how how our grid side work that will connect the data. Then we'll do the AI analysis that we have already talked about. Then we'll detect and predict the identification of thefts and anomaly detection. Then we'll take the action. Then we can see the demo of our project. Moving forward to the demo, as we can see, we have Bangalore setup that we already talking about. Here are the buildings and they are meter connected with it. We can see the orbital video view, we can see the street view, we can see the top view, we can see the ISO view that we are talking about. When we see according to building, so that is the normal theft detection. Basically, the green color shows the normal theft detection, the red color shows the high theft detection, and as we can move forward and see how many theft detection are there. The merge panel combines the demand forecasting that we have seen, the demand forecasting and the anomaly detection and the explainability. We display the current load, how it is working on. We display the predicted demands, how it will be working on, and we display the risk score, we display the confidence level and everything. So, the demand forecasting graph predicts the short-term electricity demand that we can use for the historical smart meter patterns, helping to prevent overloads and the transformer stress that we were talking about, that we had alert on it. One of the strongest part of the grid side is multi-agent architecture. As we have talked that it is not relying on the single AI model, it has using five independent specialists. Each agent analyzes the meter behavior from a different perspective, and a case is scaled according to it. For example, if we take an example for like consumption is deviated significantly for a peer household and the feeder misbalance came, so we the platform make it auditable and trustworthy for the real development. So we support CSV and Excel. Okay. So as the data is uploaded, the AI pipelines will dynamically update its risk classification, its anomaly it detects, as we can see in the hour zone. And we have grid health goals, and we have 24-hour consumption, how it is working. Of course, it is off the dummy data, but it is installed, it is taken from the backend, and we have the AI alert zone, and thus the grid site transform the smart meter data from a passive record to the proactive operational intelligence that we were talking about. As we can see a data that is for Rajinagar, the load voltage is 126 kilovolt and the voltage is 226 volt. Anomaly is 100% because thefting is possible at 2% and we can see it is showing the high risk area. And as we come person to the low risk area, that is for Coromandala, the load is 266 and voltage is used 228. That is okay. And anomaly is 44. Theft probability is 14%. That is for medium risk role. And for the normal one, we have theft probability of 0 and we have load of 175 kilovolt and we have voltage of 237 volt and we have anomaly of 19 by 100. And we can see how this data is coming basically. If we go through, we can see and we reload this site, the data, the summary, the JSON format that is coming from here, the zones which are they are in, they are coming from my AI resources, and the alerts message that we are talking about and how it will give it, and the theft cases also accordingly. There are two theft cases as we can see, and all the building areas. As we can see, the AI demand forecast that has been first we had grid that we already told about the 24-hour consumption and the grid gauge and the anomaly detection according to the different areas at different hours. Then we have AI predict model that will predict accordingly next 24 hours what are the high risk zone, what is the forecast accuracy, and where the more theft cases and more voltage consumption would be there. And of course, we have anomaly of how many flags are there, how many meters are that has been thefted according to the our AI, and it will accordingly give the data to the learning model, and thus we can know in the different in the upcoming future that of course these areas are more theft prone, so we can do changes while further in it. Overall, it was a nice experience building it. I'll just understand how the grid site operators work, how the theft and anomalies are very common in it, and how the smart vehicle works. Overall, I believe our architectures enable a simple anomaly detection as and the function of the completely AI-driven operation intelligence layer. And I believe our model would work best with the BESCOM operators, and it would be helpful to them to identify either the theft detection, that was the major problem that we've already discussed, either the we have the issues like the no early warning for the demand spikes, and we can see and how the AI layer would work. It will have data ingestion, validation, it will have per demand baseline, zone scaling, everything. And we can see how even the flags or even the thrown prone areas we can detect easily and work it for, as the our AI has five independent signals that we have checked, and each are for the best in their purposes. And thus, I enjoyed in working phases, and I would like to work further on it. And thank you for giving me this opportunity for working Westcom.